Okay, we can start. Any questions? I'll probably, yeah, hopefully the grades, should give them to you around Tuesday of next week, I would say. So, yeah, once they are posted, I'll send an announcement to the hopefully they send them, but I mean, just kind of the same thing that, but, we should see. Today, we are switching topics a little bit. We're talking about the determinant, which is a cool a cool thing to learn. I think it's kind of useful. So, a determinant of a square matrix. Basically, the idea that I have is spend today's class talking about the determinant of a 2 by 2 matrix. And then next time we'll talk about like the general case. Like a lot of the philosophy of this class is like, if you understand what happens with 2 by 2 matrices, you kind of understand what happens in any general case. It's just like, because the other sizes are bigger, like there's more algebra involved. But so it's good to spend like some amount of time just like making sure that like the 2 by 2 case is okay. And then like next time we'll discuss the general case. So let's talk about the 2 by 2 case. Okay. So here's a thing that we can start with. There are many ways to discuss what a determinant is. I'll try to do it like the more geometric way, just because I find that more like interesting. But like rather than just giving you like the formula from the very beginning. So it just will take a little bit of time to get to like the main formula, but that way you kind of understand what's going on, which is a little bit more useful than just having like the formula. So, so for today, just to be consistent, I will just write every vector as a column vector. So there's this vector, which I don't know if I got given you this name before, but there's this vector on the xy plane called the vector E1, which is which is 1, 0. I mean, usually I would just write this as 1, 0, but now I'm writing everything as a column vector, right? So this is a vector which you may have seen in your physics classes, which is usually called the vector I, if it looks familiar. So it's just like a vector in the direction of the x-axis, right, of length 1. That's it. Okay. And then there's this vector, like the analog of this, which we can call E2, which is a vector 0, 1. Again, I'll usually write this as 0, 1, and that's just like a vector of length 1 pointing along the y-axis. And again, in your physics classes, or if you took multivariable calculus, this is what the vector J is. This vector is usually called J, right? So typically this is like J, and there would be a third one, which is K, if you have like the z-axis, right? Now, so with these two vectors, what you can do is make a square, right? Which you see here. Right, and so I mean this is kind of like the unit square, right? Because it will have area 1 because each side has length 1, right? So this would be the unit square. So the area is 1. Okay. Now you'll see why this is related to this in a moment. Let's say that I have a 2 by 2 matrix, right? Back to the diagrams from the beginning of the semester. Let's say I have a 2 by 2 matrix like A. Oh, I'll show you. Let's see. And well, it won't. It would look kind of weird, so I'll just write it. It won't. Okay, it won't make a difference, but I'll write it in a usually I have it written this like A, B, C, D. I'll just write it A, B, C, D. Like I mean, it's kind of the same how you label the entries, but it's more, maybe it will make more sense for what I'm about to do next. Okay. So imagine that you fed E1 to the matrix, right? And by that, I just mean that you're going to do the multiplication of A times E1, which is AB BD times E1, but E1 is 1, 0. Anyone can tell me? It's a quick calculation because like the coefficients of the vector are pretty easy. What do you get when you do this multiplication? Yeah.
A and then B.
Yeah. So and what is AB in terms of the matrix?
The first column.
It is the first column, right? So here, this is like the first column of the matrix. That making sense? And well, like now you imagine that like something similar would happen if you do it with E2, right? So if you had taken E2, right? 0, 1, and you feed it into oh, let me put the diagram here. If you feed it into the same matrix, right? A, B, C, D. So now you get A, E2, which is A, B, C, D times E2, which is 0, 1 now. And yeah, it's kind of the same calculation, but now you will get CD as the answer. Sorry. Does that make sense? So far, so good. So the kind of like in terms of like of these vectors, what you can think of, if you want to think of what's happening more pictorially, right, is that let me write this do this picture again. So here you had E1. Okay, so E1, we saw that if you feed this into the matrix A, right? If you apply the matrix A to it, you just get like this vector, which is AB. I don't know where AB is going to be like, so let me just draw it somewhere in the first quadrant, however it looks like. So let me put it here. Right, so what I'm trying to say is that this vector, right, was transformed. Oh, it's also here. This vector was transformed to a new vector, which we don't know where it is. So just for like visualization purposes, I'm drawing it somewhere on the first quadrant, right? Even the length could be different. So this one had length 1, maybe this one has length 3 or 1/2. Like many things can change about the vector, right? So it's just like a new vector. Okay, and this vector E2, right, if you, again, like apply the matrix to it or do the matrix multiplication, it's going to produce a new vector on the plane. We don't know where it is, so I just have to draw the picture somewhere, right? So let me put it here. So this is like CD, which is AE2. Is that making sense? So far, so good? But so if you think about what happened here, like so on this side, I had drawn the unit square, right? Right. But if you follow what's happening here, like you can try to do like a similar picture, but instead of drawing now a square, right, you would have to draw something like this. That makes sense? What's the name of figure of this sort? It's just like called like a parallelogram, right? So this would be like what I'm trying to say is that the matrix turns this unit square into a parallelogram, right? So this is now a parallelogram. Okay. And because you see, like, you even change the angle, maybe there was a 90-degree angle here. Like now I'm making it look like if it were acute, not necessarily 90 degrees, it actually could even end up being bigger than 90 degrees. It could be like, the angle between the new vector. So it's just like some random parallelogram. And it has some area, right? We don't know what that area is, but that area is called the determinant of the matrix. So the determinant of the matrix is the area of this parallelogram. So it has some area. With an area called equal to what we'll be called the determinant of A. Okay. Which is called why it's called determinant of A? Because like A is kind of determined by the matrix, right? Because these two new vectors are basically just the columns of the matrix A. So the this like parallelogram is really determined by the matrix. So the determinant of a 2 by 2 matrix is just essentially the area of the parallelogram of this sort. Okay. Is that making sense so far, so good? Any questions about this? Okay, so it is more like what I just said, it is like 95% correct. There's something that could have been slightly different in this picture that I just made, which we have to address. So like there are other kind of two like natural pictures you could have tried to draw. Okay. I wrote it on the notes. Okay, so this is like let's call it option one. It's kind of like the first thing of like the first possibility for this picture to look like. Okay, there's another like there are actually two other reasonable things you could have drawn here. I don't know if anyone wants to give it a shot. Yeah.
The two vectors are like parallel to each other.
Right. It could just have happened that when you draw these two new vectors, they actually like there's no angle between them. Right, so like they just collapse to like a line. So option two is where like these two vectors are parallel. So like if you wanted to make like a picture, like here you still have like AB. And like I don't know, like I want to draw this orange like vector on top of it, so like you could draw it like like something like this. Is this is making sense? So what I'm trying to say in this option is like the vectors are parallel, right? These the columns are parallel. Okay, does that make sense? But I still kind of want to go with this definition that this kind of should be like the area of the parallelogram. But now you kind of like flatten it out to like, you collapse it to a line. So what should the answer be for the determinant? It should just be zero because this has no area, right? Like it's just like you just destroy the parallelogram. So it's like this is still okay, but it's kind of like a special case, like an extreme version of like area. So it's in this case, you want to say that the determinant should be zero when the vectors are parallel, okay? Because there's no parallelogram, really. Uh, since you collapse the parallelogram to a line, that's one way to think about it. So far, so good. Okay, so yeah, this was one possibility. This was another possibility, and there's actually a third one which is hidden here, which is a little bit more subtle and not like not obvious. Like you may have like like it's that this one is kind of like hard to notice. But let me see if anyone wants to give another like what else do you think could happen here?
In the negative area?
Yeah, right, but why would well okay, yes, like but in terms of the picture, how would you think this would look like?
Like, one would be, they would both be that way, maybe?
It's not so much about that, it's more like, okay. Here you have like these two vectors, right? And basically what's happening is like, from going from E1 to E2, like I just like, there's like an angle between them. I'm rotating here like counterclockwise, right? And here, like in this picture, from going from AE1 to AE2, I'm still rotating counterclockwise. So like the other possibility is kind of like the matrix screws up this order, and you kind of have to go like clockwise from AE1 to AE2. So let me try to draw it so that you see what I mean. So so essentially, what like the other thing that would happen is that AE1 kind of looks like you kind of reverse the roles of like how these vectors look like. So now AE1 is here, and then AE2 is here. So it's still like the same parallelogram, right? But if you want to move like through the smaller angle from AE1 to AE2, you see now you have to rotate clockwise. You cannot do it counterclockwise. So it's kind of like what can happen. And this is like, if you thought about like in terms of a picture, this is what you would do like on a cell phone if you like ask for a mirror image, like kind of like the matrix kind of rotates somehow, reflect like an image. This is like what's going on here, like similar to what's going on here, like or it like reverses the order in which the vectors appear. That's a better way to say it. So like what happens here is like kind of like this was like a counterclockwise rotation, right? This was counterclockwise still, right? From going from AE1 to AE2, but this one requires a clockwise rotation if you want to go from AE1 to AE2. Is that okay? So this is clockwise rotation. And it is convenient to say that the determinant here should be minus the area. So the kind of that way the determinant takes into account also like the order in which the vectors appear. So in this case, like the determinant of the matrix will actually be the minus the area of the parallelogram. That makes sense. So like roughly what I'm trying to say is that like essentially the determinant is like the area of a parallelogram, except for like maybe an annoying sign. But if it comes out negative, that just means like the matrix somehow reverse the order in which the vectors showed up when you draw them. Any questions about that? Okay, so like I'm about to give you like a formula, so just make a little bit this more concrete. It's kind of fun to find it out. So we're about to find this formula in a second, but first, it's also convenient to have like some understanding first of how this should scale. So let me write this as a rescaling property. And after that, we can find the formula. That's a kind of like a key formula. I mean, I'm going to make a picture just to make it concrete, but and then I will just give you like the formula. Let's just, I'll mostly draw option one just because it's easier to see. But let's say that you had like, let's say that the matrix like AB looks like this, and CD looks like this. Okay. And then I rescale one of the vectors. So by that, I just mean like, imagine that I make this vector 2 times as big, right? I want to make this vector twice as long. So it looks like twice as big. And let's say I make this vector just to give you like again to make it concrete. I make this a third of the original size. So I multiply this by 1/3. Is that making sense? So I elongated, enlarged, doubled one of the sizes, and what's the word by making it a third smaller? I made like one of the sizes, like the other side, like a third of the original size, right? So you shorten one, and you could also have done something where like this is twice as big and this is 7 times as big. You'll see like it is kind of, once you do the picture, you kind of will see what the answer should be like. Right. So remember, this has like an area, right? Like the area of this thing should be the determinant of this matrix. Sorry, I still keep writing them like A, B, C, D. And the area of this thing, right? Well, let's think about like just like in terms of areas, right? Like how is this area related to that area? Anyone wants to give a shot? Like what should the answer be? Like one side is twice as big and the other side is like a third of the original size. Yeah.
2/3 because you have twice the base.
Right, if I had only modified one of the sides, this would have been twice as big, right? But now I shrunk the other by a third, so like it becomes 2/3 of the original size. So what I'm trying to say is like this area, the area of the rescaled parallelogram, right? Should be 2/3 the area of the original one. Is that kind of convincing? So reasonable? Okay. But if you write this down in terms of the entries, right? What are the entries of this? I don't know if you remember at the beginning of the semester, I told you when you multiply a scalar by a vector, you just multiply each entry, right? So the entries here are like 2a, 2b, right? And the entries for this vector would be one as c thirds and d thirds, right? So what I'm trying to say is like the determinant of 2a, 2b, d thirds, right? Because that's the area of the new one, should just be 2/3 the determinant of A, B. So like just to write this in a way as a formula that's a little bit more like for memorization. What I'm trying to say is that if you multiply a column vector by the same factor, right, you can just pull out the constant. It is like kind of like taking a constant out of like an operation, like similar to like a constant comes out from an integral or derivative or something like that. The same happens like with the determinant. So like the formula that I want, like that I'm trying to tell you is that if you have if you multiply a column by a specific factor, let's call it lambda1. Right, like that means that this vector literally was elongated or shortened by this number, lambda1, and you multiply the second column by by a different factor, which could be one, by the way, like either of these like non-scalars is allowed to be one, but lambda 2. Right, so that means that the second vector was elongated or shortened, whatever, by that particular factor. Then this will be lambda 1 times lambda 2 the determinant of ABC. Does that make sense? This is one of the important formulas for today that you must memorize. So it's just saying that the determinant is it's just saying that provided each entry of a given column was multiplied by the same number, you can take it out, right? Which again, geometrically makes sense if you think about it in terms of area, because like you are just like elongating like the size by a corresponding number. Okay, is that making sense? So far, so good. Any questions about this? I mean, this also works if the numbers were negative. Like it doesn't matter like the signs of the numbers. It's just there you have to think a little bit more about. Well, now you change the order in which the vectors appears, but it's kind of like the same idea. So it's kind of here like lambda 1 and lambda 2 can be any numbers. It doesn't. They don't need to be positive sign. Just I made it that way so that the picture would be more clear. So lambda 1, lambda 2 are like arbitrary numbers. Okay. And why am I mean I only did this because now with this idea we can find like it just saves you a little bit of time when you try to find like the formula for the determinant of a 2x2 matrix. So that's what I'm about to do. Just like again in a case where it's kind of like clear what's going to happen. So let's see. It's actually like a cute thing to try. So here's like the formula, which is fun. So again, we have the vector AB, right? One of the green vector is AB. Here's EB. Okay. Now, because of this rescaling property, essentially what I'm, if these vectors like had like if this one had length 3 and length 5, essentially what you can do is kind of like how should I say this? Okay, like for example, like if you had like the vector 1, 1, right? That's like let's see. Let me put it like this. Well, let's put it 1, 1 because that's more clear. Yeah, like that. I'm about to erase this because like this is not like Is everyone convinced this is true? Right, yeah, you can just multiply back the square root inside each entry to get like an identity. Why am I writing it this way? Because if you have thought about this before, this vector has size length 1, right? It's what's called like a univector. So because of this property that you can like just take out like a constant factor, right? Like this rescaling property. What I'm trying to say is like if you were to try to find like a formula for this determinant, you can make your life easier just by assuming that the vectors are univectors, because whatever the formula is, it would just have been multiplied by the lengths of the vectors. So what I'm trying to say is that I'm going to just show you how this formula works, assuming that the vectors are like of length 1, so that I make my diagrams a little bit more simple. Because if they were not length 1, you just spit it out, like doing like a trick like this. So it's like a simplification, not to for you that you don't have to worry about it, but it's kind of why I discussed this first, so that. So what I'm trying to say, like here, like we can assume that each vector has length 1. So here, like these two vectors would be of length 1. So if this hypotenuse has length 1, right, and we call this angle theta, right? What are the entries of? I mean, how can I write A and B in terms of like theta? Anyone remembers how this works? So A, right? A would be the horizontal side. So A is this one and B is this one. Right. So what is A and B in terms of theta? Using trig functions.
Okay, cosine theta and sine.
Right. Like if this hypotenuse has size 1, and this is the angle theta, right? The horizontal side is just cosine of theta, and the vertical side is sine of theta. That's the only reason why I'm assuming that the length is 1, because otherwise I would need to be multiplying here by the length, and that's kind of annoying. Okay, everyone agrees with this. So and let's say that the angle between these two vectors are being like alpha, let's call it alpha. So now the angle between this vector and the x-axis is theta plus alpha, right? So what are the entries of this in terms of like cosines? It's the same, but with a new angle, right? Is that making sense? Because the total angle of this vector is theta plus alpha. Is that okay? Okay, and now here comes like, it's kind of magical what's supposed to happen. So it's kind of a fun thing. It's too bad I didn't bring my vectors, but let's see. This is one vector, my umbrella is another vector. Right? What happens with the area of this parallelogram if I rotate it clockwise or counterclockwise? What do you think happens with the area of a parallelogram?
Be the same.
It should be the same. Like the area shouldn't depend on like, I mean, like you see this like in your life, right? If you take this is a parallelogram, like I'm rotating it literally right now. Like what happened with, I mean, it didn't shrink, it didn't dilate. I mean, nothing happened, right? Like the area is kind of the same if you rotate it. So let's say, why would I be interested in doing that? Because like I don't know what the formula is for the area of something like this. Like maybe you remember this, but I don't remember. So I'll just rotate this so that I align the green vector with the x-axis, and now the formula will simplify a lot. So I'm going to rotate this clockwise. Now I have to do like a clockwise rotation, right? So I'm going to rotate all this picture clockwise by theta angles, by theta degrees, so that like the green vector lies along the x-axis. Is that making sense? So So rotate clockwise. By theta. So what happens when you rotate clockwise? This green vector rotated so that it's aligned with the x-axis, so it becomes what vector should I put here? What are the entries to this vector?
1.
1, 0, right? Because it has length 1, and also like a rotation doesn't change the length of the vectors, right? So this became the vector 1, 0, right? And now let's rotate this orange vector by an angle of theta. Remember the total angle of this vector was theta plus alpha, right? So what should be the new angle of the orange vector here? Just alpha, right? Is that making sense? So the entries of these vectors, like again, this one has size 1, so the entries of these vectors should just be cosine of alpha, sine of alpha. Is that making sense? Any questions? Okay, and now this hopefully is like a formula for the area of a parallelogram that you do know, because it is base, right? This is the base. What's the area of a parallelogram? Base times height, if you remember this from high school geometry. So the area should just be base times height. What is the base? What's the length of a base? It's just 1, right? Because it's like we assume that it was all unit vectors. Times the height. What's the height? The height is h, but h is kind of like, again, it's small. You see it here from the right triangle. It's just the sine of alpha, right? It's just the sine of alpha. So what I'm saying is that the area is just the sine of alpha. Is that okay? Making sense with everyone? But here's here's the other cool thing. This vector, right? This vector was produced by rotating the orange vector by an angle of theta, and we had seen at the very beginning of the class a formula for rotating a vector, if you remember it. So there was this rotation formula that said that like this, the rotated vector. I don't know if you remember like this rotation matrix. You remember this, our old friend? And I'm putting the sign here because it was now I'm doing like a clockwise rotation, not the counterclockwise. So if you keep track of what happened, like the sign should be negative. But that's not too important. What I'm trying to say is that actually this can be found in terms of the original vector this way. So what I'm saying, like I took the orange vector, which had entry CD, rotated by an angle of theta, and this is like the formula for the rotation. And if you do that, like that gives you like that tells you that sine of alpha should just be what? Minus sine of theta times c plus cosine of theta times d. But what is sine of theta? That's just b. So this is minus b times c. And what is cosine of theta? That's just a. So this is telling you that the sine of alpha is AD minus BC, and that's the formula for the determinant of a 2x2 matrix. Okay, so let me write that down. I mean, if you didn't follow all of the derivation, that's totally fine. I will just give you like God-given formula, but this is like how it comes from, where it comes from. So the other important formula for today is that the determinant of ABCD is just AD minus BC. Okay. So if like I'm about to write some examples, it's super easy to compute, but it just means multiply the elements in the first diagonal and subtract the product from the second diagonal, right? So this AD is this one, and EB is this one. Okay.
So then you could say the determinant of the transpose should be the same thing.
Right, from here, that's a good observation. So yeah, now we can start making some observations. So let me do some examples and then I'll give you some properties, right? So like just quick examples because computing the determinant of a 2 by 2 matrix is super easy. That's not a problem. The thing that's a little bit more intricate, which I'll give you next time, which will just be like a God-given formula because it does take a lot of more time to find out. It's like the determinant, like say of a 4 by 4 matrix or like a 5 by 5 matrix. The good thing is that you can always like find it in terms of like the 2 by 2 case. So once you understand the 2 by 2 case, you can sort of build up from it to find every other case. But so for example, like the determinant, like yeah, I'll say like 2, 4, -1, or let's start here with something like this. Would be that first diagonal, you multiply their entries, so it's 2 times 3 minus second diagonal, 4 times 1, right? So that's 6 minus 4 would be 2. Okay. Or like for example, if you did like, I mean, there are not that many things you can try. Like you just put like a couple of different numbers to convince yourself that you're doing it fine. But if you do something like this, it's 3 times 7 minus and then 2 times -4. So just notice that there's always like a minus in the formula for the determinant. So 3 times 7 is 21, and then minus becomes plus, right? So it becomes plus 8. So it's 29. Okay. And so the fact that like these two determinants were positive is telling you that in the picture version of this, like it didn't change like how the vectors appear, like it didn't change the rotation or the orientation. That's actually how it's called. But if you take something like, if you take something like this, you get like 1 times 3 minus 1 times 3, right, which is 0, which is kind of clear, right, because these were like parallel. I mean, maybe it's kind of like this is just 3 times the original one, so they're just parallel vectors. So this is fine. Like this is telling you that this had area 0. And like if you take something more like if you take this one but reverse, like if you just put column one in the place of column 2 and things like that, so you do 4, 3, 2, 1, right? You just flip the order of the columns. That should affect like the rotation of how they appear. So like you get 4 times 1 minus 3 times 2 until you get 4 minus 6, so you get -2. So it's minus this form, minus this one, which will be true in general. So next time I'll give you a bunch of properties of the determinant, and one of the properties will be that if you like, just change your mind of which regarding whether it's column 1 or column 2, like then the determinant will change signs. But it does make sense in terms of the picture because you're just like relabeling what's the second column or the first column. So the rotation, like this convention about moving clockwise or counterclockwise had to change in the picture. That making sense? And like kind of back to what you were saying. What's it? Right. So if A was like A, B, C, D, right? What would be A transpose? A transpose would be A, C, B, D, right? You just change the rows with the columns. But if you find their determinants, right? The determinant of A is AD minus BC, but that's also like the determinant of the transpose, right? There's no, I mean, in terms of the determinant, there's no difference, which is not so clear. Like if you think about it, just like in terms of the original definition, right? Like the why this would have been the case, right? So in this case, like, and this is actually going to be true for any size of matrix, like not just like 2 by 2. But I'll give you that formula. Okay, so what makes the determinant really, I mean, so far, like, so I have told you that the determinant is this thing related to the area of a parallelogram. That's fine, but it doesn't necessarily tell you what this is useful for us, right? I mean, unless you were interested in finding areas for some reason. What makes this useful is that there's like a very elegant formula for the determinant of a product of two matrices. And that's really what makes this thing work well. So let's try to find out the determinant of A times B. And once we understand that, then we really can do many useful things with the determinant. Before then, like it doesn't like it's called, oh, we can call it like a product formula, but like what we'll try to show you is like the formula for like one way to do it, which is the boring way, is like, well, you give like names to the entries of the two matrices, right? This is like A, B, C, D, and the other way like E, F, G, H, whatever. Do the product, compute the determinants, blah blah blah, and then to see if you find something useful. That's like not like the way to go. Like the way to go is kind of trying to make a picture to see what's going on. And again, like this is kind of like a derivation. Like there are not many derivations that I want to do in this class because don't try to do it too theory oriented, but it is kind of like one of the few ones that maybe kind of makes sense to try to show you to see so that you get like a good idea of like how this works, because again it's kind of very elegant, but after that, like I'll just give you the formula and then you can just use it. So that's this is why I have started with this picture of like of the unit square. I think the E1 was a green vector, right? So these were like our two original vectors, right? Like the unit square. And again, if you think about it as a process, when we apply the matrix A, let's see how I'm drawing this. This became A E1, right? And the other one became A E2, right? Became a new parallelogram. And this, I mean, again, I'm just doing the picture in the case that's easiest to understand. Everything else works when you start thinking about all the other possibilities. So this one had like area equal to the determinant of A, right? Like that's the whole point of. Okay, let's see how. But if you like, this is why at the beginning of the course I also talk about this perspective. What did this mean? It meant apply first the matrix A to a vector and then apply the matrix B to a vector, right? So imagine that we apply the matrix B to this picture, right? So this vector is just going to become a new vector, right? Like, I don't know what it is going to be look like, so let me just put it here. What's this new vector? Like the one that you got from applying B to this thing. So it's like B, A, B1, right? And this vector also becomes a new vector. So like, again, like I don't want to, I'm trying to be super like precise of how the pictures look like. So I just put it here just for like illustrative purposes. And what's the vector here? It's the one that you got by applying B to this one, right? So this becomes B, A. So this parallelogram has some area that's the determinant of B times A, right? Because it is what you got from applying A and then applying B. Is that making sense? Kind of reasonable. So this one has area equal to the determinant of B times A. So far, so good. Okay, and now here, like this is like a very cool like idea. So imagine that this is a parallelogram. So imagine that I want to cover this parallelogram with squares. Okay, so do you see them there? Well, I mean, imagine I'm doing that. If they're super tiny, right? Like, who has taken calculus? Who, like, the majority of you, maybe like Calc 1 or whatever. Like, if this is super tiny, right? Imagine you really make these squares very small. Like, then you can really cover this pretty well, right? Kind of the bed, like, the smaller you can make them, right? The more you can cover this without leaving like any gaps. If that makes sense, right? Because this is like, you know, this is a square, this is a parallelogram. You cannot be, you would have to cut some squares kind of a little bit to finish like tiling the parallelogram. But it is more or less like, okay, like the area that you use to cover them is really small. Like that's like the calculus part because I'm talking about something which is super small. So let's say that this one had like area, this is like a tiny square of area epsilon squared, right? So each square has like size epsilon. So length times like what's the area of a square is like base times height. So like the area would be epsilon squared. And if this is like a very good like very small if this is like this is covered with like very small squares, like there's almost no gap between what you get by covering with squares and like all the area of the parallelogram. So like just to make this very concrete, imagine that the area of the parallelogram had been 100 square meters, right? So this area was 100 square meters and like the squares like were like of area 2, right? Like 2 square meters. So how many squares would have I needed? Simple division, right? It's just 50, right? Like so like how many of these do we need? We would need that making sense? So again, if this had been like 100 square meters, this like 2 square meters, like you would have needed 50. And the idea is like, oh, you would be like, well, but you really, yeah, again, like you cannot really cover this completely correct with squares, but I'm saying like, wow, once you make them like 0.000001 square meters, this is like a really good approximation, like for how you should cover this. So like imagine that, is everyone kind of following the idea more or less? Okay, so let's just focus on a single square here. Right? What happens with this square when you apply the matrix B to it? It just like changes into a parallelogram, right? Like the matrix B will, remember, like the matrices, what they're doing is like turning squares into parallelograms. That's how you should think of what a matrix does to a square. It just parallelogramizes it or whatever. So like it just becomes a parallelogram, right? Does that make sense? So this, I'm following what happened with one of our squares, tiny squares. What's the area? So we started with a square of size epsilon squared, right? Oh, sorry, a square of area epsilon squared. What should the area of the new parallelogram be? Anyway, this is like the key insight. Anyone wants to give it a shot?
From the B to
Yeah, because like we had said that rescaling doesn't do too much for us. So really the important thing is like this just multiplies by the determinant of B. So whatever, like this, like again, if this had been 1, it's kind of more clear, but if this had been, like, it just happens to be epsilon squared, but that's fine because the determinant has this rescaling property. Okay, but if I needed 50 here, like the same 50 are still covering this new square, this new parallelogram, it's just like I'm changing their sizes. So the same number n is still okay. So here we still need, like, you know, because like it is kind of like every one of these went code somewhere, and so it is still the same number. Like, you know, if you actually bought 50 tiles here to tile this parallelogram, you're still using 50 tiles here to tile this new one. It's just like now the tiles look a little bit more funny. So this n is still the same, but it's not like the area of this parallelogram, of the new parallelogram, which was BA, divided by the area of our squares or parallelograms. So this would be determinant of B times epsilon squared. Oops. But what is n? N is determinant of A over epsilon squared, right? Can you solve for the determinant of BA? What do you get here? Like the epsilon squares cancel? The epsilon squared cancel? You move this to the numerator, so it's just determinant of B times determinant of A. So this is like the most important property of the determinant. This is like what makes the determinant useful. That like it's kind of like a miracle because like if you think about it in terms of the original pictures, it's not so obvious, right? But it's just saying that when you multiply the determinant of a product of the matrix, is just the product of the individual determinants. And that's what makes all the theory work. Like, I mean, without this, a determinant would be completely useless. This is like what makes it like an important concept. Is that making sense? Let me tell you, right? And this actually will work for any size, like, but it's just like they're like for other sizes, you would have to make more complicated pictures, but it's kind of like the same philosophy that applies. So why would this be? This is why this is useful. So like this is the most important application of the determinant thanks to this formula. Here's an application. Well, let's say a matrix has an inverse, right? Let's say a matrix A is invertible. Let's say So what did that mean? It means that like there's an inverse matrix A inverse, right? The property of the inverse matrix was that A inverse times A gives you the identity, right? And we're still in this 2 by 2 case, but it kind of works like everywhere. Like it will work the same way for. Okay. So far so good. Let's take determinant of both sides of this equation. What's the determinant of, I'm sorry. What's the determinant of the identity matrix? It's just one, right? It's the area of the unit square, actually. Like the columns are the unit square of the identity matrix. What's the determinant of A inverse A? According to the product formula, is determinant of A inverse times determinant of A. So again, like according to this like magical formula, is that okay? So you have two numbers, right? You have two numbers whose product is 1. Like the important thing about this is that neither can be 0, right? None of them can be 0. So that tells you that for an invertible matrix, the determinant cannot be 0. So that means that determinant of A. So this tells you two things. First says the determinant of A cannot be 0. And also tells you that the determinant of the inverse is 1 over the determinant of A, right? Like they're kind of like come side by side. Okay. And this is kind of like the easiest check for invertibility of a matrix. You compute its determinant, and if it gave you 0, it cannot be invertible. Okay. Is that making sense? So what this means is that the determinant so in practice, what this means is that in practice, so if the determinant of A equals 0, then A is not. So it gives you so it like in particular case, right? I don't know if you remember like the general case, like the determinant of A, B, C, D was AD minus BC. So what that means, like, so we need these quantities to be non-zero for the matrix to have an inverse, and that kind of makes sense if you remember when I had given you like the formula for the inverse of a 2 by 2 matrix. You may remember that there was 1 over the determinant actually appearing in the formula. So that's it's kind of coming together. So this means we need determinant of sorry, we need AD minus BC if different from 0 for the matrix to have an inverse. Is that making sense? So of today, the most important things that I have said are like the formula for the determinant of a 2 by 2 matrix, the determinant of A equals the determinant of the transpose, and that if the determinant is 0, the matrix is not invertible. Okay, and I mean, like remember before the only way we had to check this was like trying to reduce this to the identity. and see whether you succeeded or not. That's like a lot of operations. Next time I'll give you like a formula for the determinant of like an n by n matrix. That I won't try to justify because it would take us an eternity. So today is kind of like the day when I try to justify like as many things I could. Like next time I'll just give you a bunch of properties of the determinant because those are kind of harder to see from this definition. So, but and yeah, and I mean this is kind of like the magic formula for the determinant. Really, it's like what like without it, it's like nothing like would be so nothing would be useful with it. So yeah, so what we do next time is I'll give you like a bunch of formulas, like just a you know. So today will be finish a little bit earlier because I don't want to start like the general case today. But just to give you like a heads up, like you know, the idea, what would be like the determinant of a 3x3 matrix? Actually, it's kind of easier for me to draw. Maybe first draw out the parallelepiped. Oh my God, this doesn't look like a parallelepiped at all. No, let me draw a parallelepiped. That's the thing I want. It is like a tilted box, right? Kind of looks like a box. So what I'm saying is like one of the you could think of well, one vector is like A, B, C. The other was like what? D, E, F. Right. And then the last one was like what? G, H, I. Right. And so the determinant of A, B, C, D, E, F, G, H, I would be kind of like the volume of this parallelepiped, which kind of like the same things like, well, maybe it's negative because when you took that unit cube and made this parallelepiped, maybe there were some counterclockwise things like rotations, like you change the order of like the convention for your vectors and things like that. But it's roughly like this would roughly be like up to a sign is the volume. It is the volume of this parallelepiped. I don't even this word parallelepiped is difficult to spell, so I'll just point to the picture. So, but many of these things that you kind of like still figure out from this picture, and like, so next time I'll just give you, and like you know, if it were like a 4x4, there's like a hyper parallelepiped thing, like you know, there's a hyper volume, whatever, and then like, it is kind of always like some sort of volume or area, the determinant. But there is a convenient formula like in terms of similar to this. So that's what I will give you next time. So, and once we have that, we have like everything in place to compute determinants of like of whatever matrix you desire. Okay. So yeah, I think this is a good place to end because I don't want to get into the general. Okay, so then when you end up a little bit earlier. So I'm going to give you like a mini quick assignment on Canvas just for you to compute some 2x2 determinants so that you are acquainted with it. And next time we'll begin with that general case.
Yeah.